Welcome back to the Deep Dive, where we take your curiosity, your study materials, and hopefully a healthy dose of wit to fast-track you to well-informed. Today we're tackling a topic that's absolutely fundamental. I mean, really core to understanding how computers truly juggle multiple tasks. It's especially vital for anyone, maybe like you, navigating the complexities of operating systems in class. We're diving deep into the intricate world of process synchronization, parts 1 and 2.
Yeah, this is a big one.
You've given us some fantastic source material, insightful excerpts from Abraham Silberschat's operating system concepts, which is, pretty much the Bible for OS concepts.
It really is a foundational text, yeah.
And also a peek into the Pintos manual, which is super cool because it gives that hands-on view of actual OS design.
Right, so we get the theory and the practice. That's a good combo.
Exactly. It helps make these ideas, well, stick.
And our mission today, really, is to make these concepts not just understandable, but to help you truly get them. We want to illuminate the why behind the what, provide those critical aha moments, maybe some concrete examples, perhaps even a bit of fascinating trivia that'll make these topics easier to remember so you can, confidently ace your upcoming classes.
Right.
Think of us as your personal navigators, maybe through the potential minefield of race conditions and deadlocks.
Okay, so how are we going to tackle this? This landscape seems pretty complex. Well, we'll start by building a strong foundation, exploring the fundamental problems that synchronization is actually trying to solve in the first place.
The why bother.
Exactly. Then we'll peel back the layers, look at the low-level building blocks like the specialized hardware support you find in modern CPUs.
Okay.
From there, we'll move up to the higher-level tools that programmers actually use day-to-day, things like mutexes, semaphores, and monitors.
The practical toolkit.
Right. Then we'll put those tools to the test, look at some classic synchronization challenges, and finally connect it all back to how real-world operating systems like Linux, Windows, even your Pintos system implement these really important ideas.
And understanding process synchronization is just so critical because really in any system where multiple things happen concurrently, whether it's on your smartphone juggling background apps.
Right, like checking email while playing music.
Exactly. Or a powerful server processing thousands of web requests, or even within a single web browser tab running some complex JavaScript, there's an inherent risk of, chaos if these operations aren't carefully coordinated.
Chaos is a good word for it.
Yeah, at its core, it's all about ensuring data integrity and efficient resource sharing. Without robust synchronization, you'd quickly find your computer system giving you unreliable results or corrupted data. Or, even worse, just completely crashing without warning.
Been there.
It's kind of the silent guardian of stability in this complex computing world we live in. 101. The fundamental need for synchronization. Why is it a problem?
So let's really set the stage then. Why is this even a problem we need to solve? Well, modern operating systems, and by that we mean everything from Windows or Mac OS X on your desktop to Linux powering servers in the cloud to the OS in your phone, they're all fundamentally designed around concurrency.
Doing lots of things at once.
Exactly. We're not just running one program anymore. We have multiple processes running seemingly at the same time, and within those processes, maybe multiple threads, all potentially trying to do stuff simultaneously.
Right.
It's like a bustling city, isn't it? Full of activity, all happening at once, and everyone needing to share the same roads, buildings, resources.
Precisely. And to connect this back, remember from earlier discussions, a program becomes a process when it's loaded into memory and starts running.
Gotcha.
And it's pretty standard now that most operating systems support processes with multiple threads. This inherent parallelism, especially clear in what we call symmetric multiprocessing or SMP systems.
Or you have multiple CPU cores.
Exactly, multiple cores, where n processes can run if there are n CPUs, as the source says. This is fantastic for throughput. It means we get way more work done in less time using all those cores.
Like video editing or big databases.
Exactly, web browsers with tons of tabs. They all thrive on this ability to do multiple things at once. But here's where the aha moment and the real challenge starts.
Yes, because when these concurrent processes or threads need to access or, crucially, modify shared data structures, like a common bit of memory, a shared variable, maybe a file that multiple tasks are looking at, things can go sideways fast.
Yeah, very fast.
The order in which they access and change that shared data isn't guaranteed.
Yeah.
Right? It depends on the unpredictable timing of the CPU scheduler.
Exactly, who gets to run when.
And that lack of predictable order can lead to unpredictable and, most importantly, incorrect results. This chaotic situation, where the final outcome depends entirely on the timing of who accessed what when. That's precisely what we call a race condition. It's a fundamental, pervasive problem that process synchronization aims to solve.
Yeah.
And honestly, it's the source of some of the most frustrating, hard to debug software bugs out there.
Oh, definitely. The source material flags this clearly. It says, problems exist, however, in the areas of protection and synchronization between the processes sharing memory when it talks about inter-process communication IPC using shared memory.
Okay.
And this is critical because while shared memory offers, as it says, maximum speed and convenience of communication because you're bypassing the OS for every little data transfer, it also puts a big responsibility on the programmer.
Right. You have to manage it yourself.
You have to carefully manage that shared access. Imagine two threads both trying to increment a shared counter variable. Let's call it count.
Right.
Like count is 10. And both threads try to read count, then increment it, then write count back. You'd expect it to become 12, right?
Logically, yeah. 10 plus 1 plus 1.
Right.
Hmm.
If they both read 10 at roughly the same time, then both increment their private internal copies to 11, and then they both write 11 back to the shared count variable.
Ah, the final value is 11, not 12.
Exactly. The second write overwrites the first one. That's a classic race condition causing data corruption. One of the increments just got lost.
Okay, for a simpler analogy, maybe, think of multiple cooks trying to add different ingredients to the same mixing bowl simultaneously with no coordination.
Right, like a kitchen nightmare scenario.
Yeah, one cook is trying to add flour, another's adding water, maybe a third is pouring in salt. Now imagine a specific recipe step. Add 1 cup flour, then 12 cup water.
Okay, sequence matters.
Right. If cook A starts adding flour, but cook B interrupts them halfway through to add the water, and then cook A finishes adding their flour, the recipe's messed up.
Yeah, the proportions are all wrong.
Exactly.
Yeah.
Depending on who got there first or who got interrupted by, I don't know, a phone call or whose hand was physically in the bowl at what exact moment, you might end up with way too much salt or not enough flour or just a complete mess.
Mm-hmm.
The final dish isn't going to be what anyone intended because the order of operations wasn't controlled. That's a race condition in the kitchen. And that's why we need rules like only one person touches the bowl at a time.
And to prevent these race conditions, to ensure that data consistency, we need a very specific mechanism. When one process or thread is modifying shared data, no other process or thread can be allowed to access that same data reading or writing until the first one is completely finished.
Okay.
That segment of code where the shared resource is being accessed, that critical moment where the cook has their hands in the mixing bowl that's known as a critical section.
Gotcha. Critical section. That's the danger zone.
Exactly. And the core challenge of synchronization is, how do we enforce this restriction programmatically? How do we ensure only one cook has their hands in the bowl at a time?
Right. And when we're trying to design a solution for this critical section problem, there are 3 absolute, non-negotiable requirements. Any robust solution must satisfy these. They're like the golden rules.
Okay, what are they?
First, mutual exclusion. This one's pretty straightforward. Only one process or thread can be executing inside its critical section at any given time.
Makes sense. No 2 cooks in the bowl at once.
Right. If you don't have this, you're right back to race conditions.
Got it. Rule 1, exclusivity.
Second, we need progress. This means if nobody is currently in their critical section, and some processes do want to get in, then the decision of which process gets to enter next cannot be postponed indefinitely.
Okay.
And critically, only those processes that are actually ready to enter, meaning they're not off doing some other non-critical work in their remainder section, can participate in making that decision.
So the system has to keep moving, can't just freeze if the resource is free and someone wants it.
Exactly. You can't have a situation where the resource is available, people want it,
Yeah.
but nobody gets chosen to go in. Progress must be made.
All right. Rule 2, keep things moving.
And third, bounded waiting. This one is about fairness. There has to be a limit, a bound on the number of times other processes are allowed to enter their critical sections after a particular process has made a request to enter its own critical section, but before that request is actually granted.
So no cutting in line forever.
Precisely. You can't just keep letting other processes jump ahead indefinitely while one process waits and waits and waits. Without this, some processes could effectively starve, never getting their turn to access the shared resource.
Okay, that makes sense. Fairness is important too. Rule 3, bounded waiting.
Yep, mutual exclusion, progress, and bounded waiting. These 3 together define what makes a solution to the critical section problem correct and fair. If you violate even one, your synchronization mechanism is fundamentally flawed. Money, too. Low-level solutions, hardware and software approaches.
Now, historically, before we had all the fancy hardware support we have today, computer scientists actually wrestled with this problem. It's kind of amazing to think about.
Yeah, how did they even do it back then? Without special CPU tricks.
Well, imagine trying to coordinate those cooks in the kitchen purely by shouting instructions back and forth. No physical barriers, no stop signs, no timers, just logic.
Sounds error-prone.
It was. But their early software solutions proved it was possible. Decker's algorithm was a notable early one, but it only worked for two processes. Still, quite complex, involving flags and turn variables.
Wow, just for two.
Yeah, but it worked. And then Eisenberg and Maguire extended these ideas to work for end processes, which was a big step. They even formalized things like a lower bound on weighting of N1 turns for fairness.
So they were really thinking about that bounded weighting rule even then.
Absolutely. These were crucial steps, laying the theoretical groundwork. Even if modern systems use more efficient hardware methods now, the ingenuity back then was incredible. It really shows how deep the problem is.
Okay, so those software solutions were clever, but probably complex and maybe slow, right? Did engineers eventually look to the hardware itself for a faster, more fundamental fix?
They absolutely did, because relying purely on software logic that could be interrupted at any moment was tricky. Modern systems heavily rely on special hardware instructions specifically designed for atomicity.
Atomicity, meaning uninterruptible.
Exactly. Operations guaranteed by the hardware to complete entirely as a single unit without any interruption. And the compare and swap instruction, often abbreviated CAS, is a fantastic example of this.
Okay, compare and swap. How does that work?
It's a single, uninterruptible operation. It atomically, meaning all at once, compares a value currently in a specific memory location with an expected value you provide. If they match, and only if they match, it then swaps the value in memory with a new value you also provide.
So it checks and updates in one go, without anything else getting in between.
Precisely. It's all or nothing, one swift, unbreakable action executed directly by the CPU hardware.
That sounds powerful.
It is. The source defines it like this.
Oh.
In compare and swap, int value, int expected, int new value. It works by returning the original value that was in memory before the potential swap. So if the value it returns is equal to the expected value you gave it, that tells you, yes, the comparison succeeded, and I just put your new value into that memory spot.
I see. And if it returns something different?
It means the value in memory wasn't what you expected, so the swap didn't happen. The brilliance here is moving that critical check-then-update step from potentially interruptible software right into the CPU's fastest, most reliable circuits. It's the bedrock for nearly all modern synchronization tools.
How would you use it for, say, a simple lock?
Good question. The source shows exactly that. You could have a global lock variable, maybe initialized to 0, meaning unlocked.
Okay.
The first process wanting to enter its critical section calls compare and swap and lock, and expects the lock to be 0 unlocked and wants to set it to 1 locked.
Right.
If lock was 0, the CAS succeeds. It writes 1 to lock, and it returns the original 0. The process sees it got 0 back, knows it acquired the lock, and enters its critical section.
Makes sense. What if another process tries right after?
If another process then calls compare and swap and lock 0, 1, it will find that lock is now 1. So the comparison lock equals 0 fails, the swap doesn't happen.
And what does CAS return then?
It returns the current value, which is 1. The process sees it got 1 back, not the expected 0, and knows it failed to acquire the lock.
Gotcha. So it has to wait or try again when the first process is done?
It simply sets lock equals 0 directly, making it available again.
And here's a crucial insight, maybe a bit of trivia for you listening.
Mm-hmm.
This type of lock, where a process just keeps checking that lock variable in a tight loop until it becomes available.
Mm-hmm.
It's often called a spin lock, because the process literally spins in a loop, burning CPU cycles, just waiting and checking, waiting and checking.
Or constantly polling that variable.
It's incredibly fast if the lock is held for a very, very short time, like just a few CPU instructions.
Right.
But it can waste a ton of CPU cycles if a process has to wait for a longer period, just sitting there spinning, doing nothing productive.
Exactly. The source calls this busy waiting, and it highlights it as a particular problem, especially in single CPU systems.
Why especially there?
Because if you only have one CPU and the process holding the lock needs that CPU to finish its work and release the lock, the spinning process is actively preventing the lock holder from running by consuming all the CPU time.
Ah, deadlock by spinning.
Sort of, yeah. It's just pure waste in that single CPU scenario.
That's an important distinction, though. Busy waiting sounds bad, but you said spin locks are used.
They are. In scenarios where the critical section is extremely short, especially on multi-core systems, SMP,
Why multi-core?
because on a multi-core machine, if one core is spinning, waiting for a lock held by another core, that other core can still make progress. And the overhead of putting a thread to sleep and waking it up later, a context switch, can actually be much higher than just letting it spin for a few microseconds.
I see. So for very short waits on multi-core systems, spinning is faster than sleeping waking.
Exactly. Kernels use them a lot for these ultra-fast, microcritical sections, but it's a trade-off. And interestingly, the PENTOS manual specifically warned you against using busy waiting in your project submissions.
Ah, so they want us to use more efficient methods for potentially longer waits in our student projects.
Precisely. It drives home the point that you need to choose the right tool for the job. Busy waiting has its place, but it's often not the right answer, especially in a general-purpose OS context like PENTOS, maybe 3, higher-level abstractions, mutexes, semaphores, and monitors.
Okay, so building on those hardware primitives like compare and swap, and trying to avoid the pitfalls of things like busy waiting where possible, we move up to higher-level synchronization tools. These are generally easier and safer for programmers to work with.
Right, abstracting away some of that low-level complexity.
And mutex locks are often considered the simplest, most fundamental of these. The name itself, mutex, gives it away, right? Short for mutual exclusion.
Yep. It provides that basic guarantee we talked about. Only one thread in the critical section at a time. It's like having a single key for a room, only the person with the key can go in.
So how do they work conceptually?
Well, a mutex typically has two fundamental atomic operations, acquire and release. A process calls acquire before it enters its critical section.
To get the key.
Exactly. And then it calls release after it exits.
To give the key back.
Right. And the key difference from a simple spin lock is what happens if you try to acquire the mutex when it's already held by someone else.
What happens? Does it spin?
Usually not, it blocks. This means the process stops executing, the operating system changes its state to waiting, maybe puts it in a queue for that specific mutex, and then schedules some other process to run.
So it yields the CPU instead of wasting it spinning.
Precisely. That's the big advantage for critical sections that might take more than a few microseconds. The source gives a simple conceptual definition. Acquire checks if an internal available flag is true, sets it to false, and proceeds, release, just sets available back to true. But the implementation uses mechanisms to block and unblock processes efficiently.
And it's absolutely crucial, I assume, that those acquire and release operations themselves are atomic. You can't have a race condition on the lock itself.
Oh, absolutely critical. If two processes tried to check available and set it to false at the exact same time, you'd break the mutual exclusion. So these higher-level mutexes internally often rely on those hardware primitives we just discussed, like compare and swap or similar atomic instructions to ensure their own operations are indivisible.
So it's layers of abstraction. Hardware atomics guarantee the mutex operations are atomic, and the mutex operations guarantee the user's critical section is exclusive.
Beautifully put, yes.
And tying this back to PENTOS again,
Yeah.
you mentioned seeing functions like lock release and lock held by current thread.
Right. And the PENTOS lock release function has a specific rule. The thread calling release must be the thread that currently owns the lock.
Safety check. So I can't accidentally release a lock that someone else is holding.
Exactly. It prevents a whole class of nasty bugs. And lock held by current thread, well, that just lets you check if the currently running thread is indeed the owner of the lock. These details show that mutexes in real systems have these important safety features built in. They aren't just theoretical concepts.
Okay, so if mutexes are like that single key lock, what about semaphores? You mentioned them being more versatile.
Yeah, if a mutex is a key, a semaphore is maybe more like a bouncer at a club who has a counter clicker. They're more robust and flexible in some ways.
A bouncer with a counter. How does that work?
Okay, so a semaphore, let's call it S, is basically an integer variable. But you don't just read or write it directly. You only access it through two specific atomic operations.
Wait.
And signal.
Wait and signal.
Yeah.
Okay.
Historically, wait was called P from the Dutch proberen to test, and signal was V from verhogen to increment. You might still see P and V sometimes.
T and V. Got it. So what do wait S and signal actually do?
Wait, S first decrements the semaphore value S. Now, if S, after being decremented, becomes negative, that means the resource it's guarding isn't available. The bouncer's clicker went below 0.
Okay. So what happens to the process?
It blocks. Just like when the mutex, it gets put into a waiting queue associated specifically with that semaphore S, and the OS schedules someone else.
Right. And signal S.
The signal S increments S. Now, if S after being incremented is less than or equal to 0, that means there were processes waiting in that queue because the count was negative or 0 before the increment.
Ah. So incrementing it means a resource just became available, or we satisfied a waiting condition.
Exactly. So the signal operation then wakes up one of the processes that was blocked in the semaphore's waiting queue, moving it to the ready state so it can eventually run again.
Okay, that's clever. So wait potentially blocks, signal potentially unblocks someone else.
Precisely. And again, the key is that processes block without busy waiting, allowing other useful work to happen.
And so you said they're versatile. How so?
Well, the brilliance is that semaphores can act in two main ways. They can be binary semaphores, where the value is restricted to only 0 or 1. In this mode, they behave almost exactly like mutexes, ensuring mutual exclusion.
Okay, a 0-1 semaphore is basically a mutex lock.
Pretty much. But they can also be counting semaphores where the integer value can be any non-negative number.
Uh-huh. Like your bouncer counting people in and out.
Exactly. This makes them perfect for managing access to a pool of multiple identical resources.
Huh.
Imagine you have, say, 5 printers available in a system.
Go.
You can initialize a counting semaphore to 5. Each process wanting a printer calls wait. This decrements the count. As long as the count is positive, they get a printer. If the count hits 0, the next process to call wait blocks.
Until someone finishes printing.
Right. When a process finishes, it calls signal, which increments the count, potentially waking up a waiting process if the queue wasn't empty. It elegantly manages access to that pool of 5 printers.
That is versatile.
Yeah.
Much more than just a single lock.
This flexibility also introduces potential complexities. One subtle but critical issue that can arise, especially with semaphores used for resource locking, is priority inversion.
Priority inversion. What's that? Sounds bad.
It is bad. Imagine you have 3 processes: high priority, medium priority, and low priority.
Okay, HML.
Now, suppose the low priority process, L,
Mm-hmm.
acquires a resource, maybe using a semaphore or mutex, that the high priority process, H, also needs, so L has the lock.
Right.
Now, H comes along, tries to acquire the same lock, finds it held by L, and H blocks. Which is expected, H has to wait for L.
Okay, H is waiting for L. Seems normal so far.
But now, while L is still holding the lock and H is blocked, the medium priority process, M, becomes ready to run, since M has higher priority than L.
The scheduler runs M instead of L.
Exactly. The scheduler preempts L and runs M, and maybe M runs for a long time, or maybe other medium priority tasks keep running. The result is that L, the process holding the lock that each needs, never gets enough CPU time to finish its critical section and release the lock.
So H, the high priority process, is effectively blocked by M, a medium priority process, indirectly.
Precisely. That's priority inversion. The high priority task gets stuck waiting for a low priority task that can't run because medium priority tasks keep cutting in. This can wreck real-time systems where deadlines are critical.
Wow, that's subtle. Has this actually happened?
Famously, it crippled the Mars Pathfinder mission back in 1997. A high-priority communication task was blocked waiting for a mutex held by a low-priority meteorological data-gathering task.
No way.
Yes, and intervening medium-priority task kept preempting the low-priority task, preventing it from releasing the mutex. The whole system kept resetting due to watchdog timers expiring because the high-priority task wasn't making progress. They actually had to patch the software remotely on Mars to fix it.
That's incredible. A synchronization problem almost doomed a Mars mission. So how did they fix it? How do you solve priority inversion?
The common solution is a priority inheritance protocol.
Okay, what does that inherit?
Think of it like giving the slow truck temporary flashing lights. When a high-priority process, H, blocks waiting for a resource held by a low-priority process, L, the system temporarily boosts the priority of L up to the priority of H.
Ah, so L now runs with H's high priority.
Exactly. This allows L to run without being preempted by those medium priority tasks. It can finish its critical section quickly and release the resource.
And then H can get it.
Right. As soon as L releases the resource, its priority drops back down to its original low level. It's a temporary boost just to get that critical section done and unblock the high priority task.
That's a clever solution. Temporarily promote the blocker.
It works quite well in practice for preventing priority inversion.
Okay, so semaphores are powerful, handle multiple resources, but have pitfalls like priority inversion and maybe being tricky to use correctly. Is there anything higher level still?
Yes. Semaphores are great, but because they're essentially just integer counters with wait signal operations, it's relatively easy for programmers to make mistakes. Forget a signal, call wait twice, use the wrong semaphore.
Yeah.
It can lead to subtle deadlocks or race conditions that are hard to find.
Right. Easy to mess up the P's and V's.
Exactly. That's where monitors come in. They represent a higher level synchronization construct, often built into programming languages themselves, that bundles everything together more neatly.
Bundles what together?
A monitor bundles the shared data that needs protection, the mutual exclusion lock required to access that data, and potentially one or more condition variables for managing more complex waiting conditions, all into a single programming structure or object.
Ah, so the lock and the data live together.
Precisely. A monitor, by its very design, ensures mutual exclusion automatically. You don't typically have separate acquire and release calls visible to the programmer for the main lock.
How does that work then?
When a thread calls a procedure or method belonging to the monitor, it implicitly tries to acquire the monitor lock. Only one thread can hold this lock and be inside the monitor executing monitor code at any time.
Okay, so entry implies locking.
Right. The source describes it clearly. While in the monitor, the thread has control over all the protected data, which it may freely examine or modify. When the thread finishes its work inside the monitor procedure and exits, the monitor lock is automatically released.
That sounds much less error-prone. The locking is implicit.
It is. It forces a structured way of accessing shared data, making it much harder to forget locks or mismatch operations. This significantly reduces the potential for common synchronization bugs.
Okay, but what if a thread inside the monitor needs to wait for something? Like if it's a consumer and the buffer inside the monitor is empty, it can't just sit there holding the monitor lock, can it?
Excellent point. That's where condition variables come in, inside the monitor. These are different from semaphores. They allow a thread inside the monitor to wait for a specific condition to become true. Condition variables typically support two main operations, wait and signal, sometimes called notifier or pulse. If a thread inside the monitor calls wait on a condition variable, a REMPL buffer node empty condition dot wait, it does two things. It gets suspended, put in a queue for that specific condition, and D, it atomically releases the monitor lock.
Ah, releasing the lock is key, so another thread can enter the monitor.
Exactly. Another thread can then enter, maybe produce an item, put it in the buffer, and then call signal on the same condition variable, buffer node empty condition dot signal.
And what does signal do?
Signal checks if any threads are waiting on that specific condition variable. If there are, it wakes up one of them. That woken thread then implicitly tries to reacquire the monitor lock before it can continue execution from where it left off after the wait.
I see. So wait releases the lock and sleeps. Signal wakes one up, which then has to get the lock back.
Correct. And unlike semaphore signals, if signal is called on a condition variable and no threads are currently waiting on it, the signal is simply lost. It doesn't increment a counter like a semaphore does. It's purely about coordinating threads based on specific conditions within the monitor's protected environment.
That seems like a very structured way to handle complex coordination.
It is, and again, tying it back to Pintos, the manual explicitly mentions 8.3.4 monitors and states, a monitor consists of data being synchronized plus a lock called the monitor lock and one or more condition variables.
So Pintos uses this monitor concept directly in its design.
Yes, it shows that monitors aren't just a theoretical idea from programming language research. They are a fundamental architectural pattern used in real operating systems and libraries for managing concurrency safely and effectively. Seeing it in Pinto should help solidify how these pieces fit together. Maybe 4. Classic synchronization problems. Putting tools to the test.
Okay, now that we've got these tools, mutexes, semaphores, monitors, condition variables in our toolkit, let's put them to the test. Let's look at some classic synchronization problems. These aren't just abstract puzzles. They really represent patterns you see again and again in real-world systems.
Oh, exactly. They're like case studies for synchronization.
First up, a real classic, the bounded buffer problem, often called the producer-consumer problem.
Ah, yes. Producer-consumer. Very common.
Imagine you have one process, the producer, that's creating items, maybe data packets, tasks, whatever, and another process, the consumer, that's using those items up.
Okay.
And they're communicating through a shared buffer, like a queue or an array.
Yeah.
But that buffer has a fixed finite size. It can only hold so many items.
Right. The bounded part.
Exactly. So the core challenge is, how do you make sure the producer doesn't try to add an item to the buffer when it's already full? And how do you stop the consumer from trying to remove an item when the buffer is empty?
And critically, How do you ensure that when one of them is actually modifying the buffer, like updating pointers or copying data, the other one doesn't interfere?
Right. You need mutual exclusion on the buffer access itself, too. It's got multiple constraints.
The source material illustrates a very common and elegant solution using 3 semaphores. Each one plays a specific role.
Okay, 3 semaphores. What are they?
First, you have mutex, initialized to 1. This is a binary semaphore used purely for mutual exclusion when accessing the buffer structure itself. Only one process, producer or consumer, can be manipulating the buffer pointers or data at any given instant.
Got it. Mutex for exclusive access to the buffer internals.
Second, you have empty, initialized to n, where n is the total size of the buffer. This is a counting semaphore representing the number of empty slots currently available in the buffer.
Okay, empty counts the free space. Starts at n.
Right. The producer will need to wait on this one before adding an item.
Makes sense. Can't add if empty is 0.
Third, you have full, initialized to 0. This counting semaphore tracks the number of full slots or items currently present in the buffer.
Full count of the items. Starts at 0.
Yep. And the consumer will need to wait on this one before trying to remove an item.
Okay, mutex, empty, full. How do the producer and consumer actually use them? The order must matter, right?
Absolutely. The order is critical. Let's trace the producer first.
Okay, producer wants to add an item.
First, it calls wait, empty. This tries to decrement the count of empty slots. If empty was already 0, buffer full, the producer blocks right here.
Step 1, ensure there's space.
Then, after successfully passing wait, empty, it calls wait, mutex.
Yeah.
This acquires exclusive access to the buffer structure itself.
Step 2, lock the buffer for modification.
Now it's safe. It adds the new item to the buffer, updates any necessary pointers or indices.
Okay, item added.
Then it calls signal, mutex. This releases the exclusive lock on the buffer.
Step 3,
Yeah.
unlock the buffer.
And finally, it calls signal full. This increments the count of full slots, indicating that one more item is now available for the consumer.
Step 4, signal that an item is ready. Wait, empty, wait, mutex, add item, signal, mutex, signal full. Got it.
Perfect. Now, the consumer does the inverse sequence. What do you think it does first?
Well, it needs an item, so it must wait for full to be non-zero, right?
That's
So
perfect.
wait full.
Exactly. Wait full first. If full is 0, buffer empty, the consumer blocks here until the producer adds something.
Okay, wait for an item, then it needs exclusive access too. So wait mutex.
Correct. Wait mutex to lock the buffer.
Then it removes the item from the buffer,
Consumes the item.
then releases the lock.
Okay.
Signal mutex.
Right.
And finally, it must signal that a slot just became empty, so signal empty.
You nailed it. Wait, mutex, remove item, signal mutex, signal empty.
Wow, that specific sequence elegantly handles all the conditions. Not writing to full, not reading from empty, and mutual exclusion during access.
It's a beautiful demonstration of how semaphores coordinate both resource availability, empty, full, and mutual exclusion, mutex.
Okay, next classic problem. The reader's-writer's problem.
Another common scenario, especially with databases or shared data structures.
Here, we have processes accessing some shared data, but we have 2 types of processes, readers and writers.
Okay.
Readers only want to read the data. And the key is, multiple readers can access the data concurrently without causing any problems. Reading doesn't change anything.
Makes sense. Lots of people can read the same book at once.
Exactly. But writers want to modify the data. And when a writer is active, it needs exclusive access. No other process, not another writer, and not even any readers can be accessing the data while a writer is working.
Right. You can't have someone reading chapter 5 while another person is busy rewriting it.
Precisely. So the challenge is, how do you manage this access to allow maximum concurrency for readers, but ensure strict exclusion for writers, all while being fair?
And fairness here gets tricky. This problem really highlights that you might need to decide on a priority policy.
Like who gets preference, readers or writers?
Exactly. Should you favor readers? Meaning, as long as at least one reader is active, new readers are allowed in, even if a writer is waiting.
That sounds good for read-heavy workloads, but the writer might starve, right? It might never get a chance if readers keep coming.
That's the risk, reader starvation of writers. Or should you favor writers? Maybe once a writer arrives and wants access, you stop letting new readers in, wait for existing readers to finish, let the writer do its work, and then let readers back in.
That ensures writers get their turn, but it might reduce reader concurrency, potentially blocking readers even when no writer is active, just because a writer is waiting in the queue.
Correct. Writer priority can lead to reader starvation or reduced throughput. There's often a trade-off. Common solutions typically involve a semaphore, say D block, used by writers to get exclusive access.
Okay, writers use a simple lock.
And then you need a way to track how many readers are currently active, usually an integer variable, read count.
But wait. Multiple readers might try to update read count at the same time when they enter or leave? Isn't that a race condition?
Excellent catch. Yes, the read count variable itself becomes a critical section. So you need another mutex, let's call it mutednatics, just to protect access to read count.
Wow. Locks protecting counters that manage access for other locks, layers upon layers.
It shows how synchronization primitives compose. So a reader would typically, increment read count. If read count just became 1, meaning this is the first reader, it would then also wait, bam block, to ensure no writer is active. Then it releases mutex and goes off to read.
Okay.
When leaving, the reader would wait, mutex arc, again, decrement read count. If read count just became 0, meaning this was the last reader out, it would signal detex to potentially let a waiting writer in. Then it releases mutex arc.
That seems complicated but covers the logic, and the writer just does wait block and signal.
Essentially, yes. This structure gives readers preference, though. More complex solutions exist to balance fairness between readers and writers. The key takeaway is managing shared versus exclusive access often requires careful state tracking, protected by its own synchronization.
Okay, one more classic, and this one's a bit of a mind bender. The dining philosophers problem.
Ah, the philosophers.
Yeah.
Yes, this one is less about a direct practical scenario and more about illustrating a fundamental danger in synchronization. Deadlock.
Deadlock, where everything just grinds to a halt.
Exactly. Imagine 5 philosophers sitting around a circular table. In front of each philosopher is a plate of spaghetti, or maybe rice, the sources vary. Between each pair of adjacent philosophers, there's a single chopstick. So 5 philosophers, 5 chopsticks.
Okay, visualizing it. 5 plates, 5 people, 5 chopsticks in between them.
Now, to eat, a philosopher needs 2 chopsticks, the one on their immediate left and the one on their immediate right. They think for a while, then get hungry, try to pick up their chopsticks, eat, then put the chopsticks down, and go back to thinking.
Seems simple enough. What's the problem?
The problem arises from how they try to pick up the chopsticks. The source describes a simple, seemingly logical approach. Each philosopher, first, tries to pick up their left chopstick, maybe represented by chopsticky. Let's say they use wait chopsticky, where each chopstick is a binary semaphore initialized to 1.
Okay, grab the left one first.
Then, after successfully grabbing the left one, they try to grab their right chopstick I plus 1%, using modulo 5 to wrap around the circular table. So they call wait chopstick plus 1%.
Grab left, then grab right. Seems reasonable. What could go wrong?
Deadlock. What happens if all 5 philosophers get hungry at the exact same time?
Oh, yeah.
And they all simultaneously execute their first step. Wait, chopsticky. They all successfully grab their left chopstick.
Okay, so every philosopher is holding one chopstick.
Yeah.
And every chopstick is being held.
Precisely. Now, what happens when they all try to execute the second step? Wait, chopstick I plus 1% to grab their right chopstick.
The right chopstick is the left chopstick of their neighbor.
Exactly. And their neighbor's already holding it.
So everyone is waiting for a chopstick that someone else is holding, and nobody can proceed.
Deadlock. Every philosopher is blocked on the wait for their right chopstick. All the chopstick semaphore values are 0 because they've all been acquired. No one can eat, and crucially, no one can put down the chopstick they are holding because they haven't finished eating yet. They haven't even started. The system is completely stuck.
Wow. That's a perfect illustration of deadlock from a simple, seemingly correct algorithm. It's because of that circular dependency, isn't it? Everyone needs something the next person has.
Exactly. It demonstrates the 4 necessary conditions for deadlock happening simultaneously. Mutual exclusion, only one philosopher per chopstick. Hold and wait, holding the left while waiting for the right. No preemption, can't forcibly take a chopstick away. And circular wait, the circle of philosophers waiting on each other.
So how do you actually solve the dining philosopher's problem? You can't just let them starve.
Right. There are several classic solutions, each aimed at breaking one of those 4 conditions. One way is to break the circular wait. For instance, make one philosopher, say philosopher 4, pick up their right chopstick first, then their left, while everyone else sticks to left, then right. This asymmetry breaks the dependency cycle.
Ah, clever. Change the order for one person.
Another approach targets hold and wait. You could require philosophers to pick up both chopsticks simultaneously as one atomic action. If they can't get both at once, they get none and have to wait and try again later. A monitor could potentially implement this.
So no holding one while waiting for the other, all or nothing.
Right. Or you could limit the number of philosophers allowed at the table. For instance, only allow 4 philosophers to sit down at any time. With 5 chopsticks, if only 4 people are trying to eat, there's guaranteed to be at least one philosopher who can eventually acquire both chopsticks, eat, and release them, allowing progress.
Limit concurrency to prevent resource exhaustion. That makes sense too.
These solutions show that preventing deadlock often involves careful resource allocation strategies, breaking symmetry, or avoiding the hold and wait condition. It's a fundamental challenge in concurrent system design. 5. Synchronization in real operating systems and modern approaches.
Okay, having grappled with those classic problems, bounded buffers, readers, writers, starving philosophers, it really begs the question, how do the real operating systems we use every day, like Linux and Windows, actually handle these kinds of synchronization needs within their own complex kernels? Let's start with Linux. It's known for being robust, right?
Absolutely. Linux, being a production OS running on everything from phones to supercomputers, has a comprehensive toolkit for synchronization right inside its kernel.
What does it offer?
Well, it definitely provides mutex locks. These are used extensively throughout the kernel to protect critical sections. If a kernel task calls mutex lock and the lock is already held, the task is put into an efficient sleep state. It doesn't busy wait. It gets woken up later by the scheduler when the lock owner calls mutex unlock.
So, blocking mutexes for potentially longer waits. What about faster stuff?
For very short, latency-critical sections, especially in interrupt handlers or areas where sleeping isn't allowed, Linux uses spin locks.
The busy waiting locks we talked about.
Exactly. But the kernel developers are extremely careful to ensure these spin locks are held for the absolute minimum time possible, typically just a few lines of code. Linux also provides general-purpose semaphores, including specialized reader-writer versions of both mutexes and semaphores, giving kernel developers flexibility depending on the access pattern needed for specific data structures.
That variety makes sense. No one size fits all.
Not in a complex kernel, no.
And what's really fascinating is how Linux adapts its strategy based on the hardware it's running on. You mentioned this earlier with spin locks.
Right. On symmetric multiprocessing (SMP) machines, systems with multiple CPU cores, spin locks are fundamental. As we discussed, spinning on one core while another core holds the lock briefly can be efficient. But on single processor systems where there's only one CPU, using a traditional spin lock would be disastrous, right? Busy waiting would halt the whole system.
Yeah, the lock holder would never get to run to release the lock.
So, on these single processor systems, Linux does something clever. When code needs to acquire what would be a spin lock on an SMP system, Linux instead disables kernel preemption.
Disables preemption, what does that mean?
It means the kernel temporarily prevents any other kernel task from interrupting the currently running task. This effectively achieves mutual exclusion for that critical section on a single CPU because no other kernel code can run until preemption is re-enabled.
So instead of spinning, it just prevents interruptions.
Exactly. It achieves the same goal atomicity relative to other kernel tasks, but without the wasted CPU cycles of spinning. Once the critical section is done, it re-enables kernel preemption. It's a very practical adaptation to the underlying hardware architecture.
That is clever.
Okay.
Okay, what about Windows? How does it handle synchronization?
Windows, much like Linux, has a rich set of synchronization objects available both in the kernel and for user mode applications via the Win32 API.
What kinds of objects?
It includes the primitives we've discussed: semaphores, mutexes, and events, which are often used like condition variables for signaling. Interestingly, objects like processes and threads themselves can also be waited upon.
You can wait for a thread to finish?
Yes. All these are types of dispatcher objects in Windows terminology. Threads can block by waiting on any of these objects until the object enters a signaled state. This provides a unified mechanism for thread coordination.
Okay. And for application developers using the Win32 API?
Well, you have functions like createThread to make new threads, and if a parent thread needs to wait for a child thread to complete, it can use waitForSingleObject, passing the handle to the child thread. The parent blocks until the child finishes.
Simple enough for joining threads. What about more complex locking like readers, writers?
For user mode, Windows offers something called Slim Reader Writer (SRW) locks. You use functions like acquire SRW lock exclusive if you need to write, or acquire SRW lock shared if you just need to read. Then you release it with releases SRW lock exclusive or releases SRW lock shared. It directly supports that reader's writer's pattern efficiently.
Slim reader-writer locks. Okay. Does it have condition variables too?
Yes, Windows also supports condition variables that work in conjunction with critical sections. Windows is simpler, faster mutex equivalent, or SRW locks, allowing threads to wait for specific conditions while holding a lock, just like in monitors. So developers have a pretty complete toolkit.
It seems like both Linux and Windows provide similar core concepts. Mutexes, semaphores, condition variables, reader-writer locks, just maybe with different names and APIs.
Largely, yes. The fundamental primitives needed are pretty universal. Another important standard here, especially for writing portable code across different Unix-like systems, is the POC6 Fancy Threads API.
Ah, threads. I've seen that mentioned.
It's a standard interface for thread creation and synchronization. So if you write your multi-threaded code using threads, it should compile and run on Linux, macOS, BSD, and other PSX-compliant systems.
What synchronization tools does Threads provide?
The basics, as you'd expect. You have thread mutex in it to create a mutex, thread mutex lock to acquire it, and thread mutex unlock to release it. If you call lock and the mutex is busy, your thread blocks. Simple.
Standard mutex behavior.
Yep. Threads also fully support semaphores, seminit, semwait, sempost, and condition variables, thread condinet, thread conwait, thread consignal, thread conbroadcast, offering that standardized toolkit for application programmers to build complex concurrent applications portably.
That standardization must be hugely helpful for developers.
Immensely. It avoids vendor lock-in for core concurrency logic.
Now, you mentioned earlier that the rise of multi-core systems is driving new research. Are there alternatives or additions to these traditional locks and semaphores emerging?
Yes, definitely. While locks are powerful, they can become performance bottlenecks, especially with many cores contending for the same lock, high contention. They also introduce the risk of deadlocks if not used carefully, so researchers are exploring alternatives.
Like what?
One exciting area is transactional memory.
Transactional memory, like database transactions.
Kind of. The idea is to allow programmers to define blocks of code transactions that should execute atomically. You basically say, this group of operations needs to happen all at once, or not at all.
Okay. How does it enforce that?
It can be done either purely in software, software transactional memory, STM, or with direct hardware support. Hardware transactional memory, HDM, which some modern CPUs are starting to include. The system automatically detects if two transactions conflict, e.g., try to modify the same memory location. If a conflict occurs, one or both transactions are automatically rolled back and retried.
So instead of explicit locking, you just declare a transaction and the system figures out the conflicts and retries.
That's the goal. It potentially makes concurrent programming much simpler, as if you were writing sequential code within the transaction block. The system handles the synchronization implicitly.
That sounds almost too good to be true. Are there downsides?
It's still an active area of research and development. Challenges include handling things like I/O within transactions. You can't easily roll back printing to the screen. Performance under high conflict rates, and ensuring fairness. But it holds a lot of promise for simplifying concurrent code.
Interesting. What else?
Another important approach, especially in scientific and high-performance computing, is OpenMP.
We touched on that. It uses compiler directives.
Right. OpenMP provides a way to parallelize code, often loop-based code, using simple directives like #pragmaompparallel4. It handles the thread creation and workload distribution largely automatically.
But what about synchronization within those parallel regions? If multiple threads need to update a shared sum, for example.
OpenMP provides synchronization directives too. The most basic is #pragmaompcritical, if you put this directive before a block of code.
Only one thread can enter that block at a time.
Exactly. It behaves just like a mutex or a binary semaphore protecting that critical section. The OpenMP runtime library manages the underlying lock automatically. There are also directives for atomic updates, #pragmaompatomic, which are often more efficient for simple operations like incrementing a counter.
So OpenMP tries to abstract away both the threading and some of the basic synchronization.
Yes, for common patterns. It's very powerful for data parallel tasks, but for more complex, irregular synchronization patterns, you might still fall back to threads or other explicit methods. It's great for its target domain, though.
Okay, one last area. You mentioned functional programming earlier as a completely different approach.
Yeah.
How did that avoid synchronization issues?
By fundamentally challenging the idea of shared mutable state. Functional programming languages often emphasize or enforce immutability.
Immutability data, once created, cannot be changed.
Correct. If data structures cannot be modified after they are created, then there's simply no possibility of two threads racing to update the same piece of data simultaneously.
Huh. So if you want to change something, you actually create a new version with the change.
Exactly. Instead of modifying data in place, you produce new data. This might sound inefficient, creating lots of new objects, but modern functional languages use clever techniques like persistent data structures, where creating a new version shares most of the structure with the old one, making it surprisingly efficient.
So by avoiding shared mutable state, you sidestep a whole class of race conditions entirely.
Precisely. You eliminate the need for locks to protect data modifications because data modifications, in the traditional sense, don't happen. Concurrency becomes much simpler because threads are operating on their own immutable data or creating new immutable results. It's a different paradigm, but very effective for building robust concurrent systems. Outro.
Wow. Okay, we have covered a ton of ground today. Seriously, deep dive achieved, I think.
We definitely went through a lot, yeah.
From really understanding why we need synchronization, mutual exclusion, progress, bounded waiting to digging into the hardware details like compare and swap,
The atomic building blocks.
then climbing up to the abstractions programmers actually use. Mutexes, those versatile semaphores, the structured approach of monitors.
And seeing how they connect, like in Pintos.
Exactly. Seeing how these ideas show up in Linux and Windows, in the thread standard, and even in your Pintos environment that really bridges the gap between the textbook theory and, actual running code.
And hopefully some of those aha moments clicked, like connecting the dots between low-level busy waiting with spin locks and why higher-level blocking mechanisms like mutexes or semaphores are often more efficient overall.
Yeah, understanding that trade-off.
We're seeing how the simple dining philosopher setup can lead to total deadlock, really driving home why careful design and resource allocation are so critical.
Right. That image is stuck in my head now. 5 philosophers, stuck forever.
And understanding priority inversion, remembering the Mars Pathfinder story, that's a key insight into the subtle ways scheduling and resource contention can interact, sometimes disastrously.
Yeah, those details matter. It's not just about making it work most of the time.
It's about making it work correctly all the time under all possible timings.
Absolutely. And those classic problems we walk through, the bounded buffer, readers, writers, dining philosophers, they really aren't just academic exercises, are they? They are like blueprints, templates for countless real-world concurrency situations you'll face when designing software.
Definitely. Producer-consumer patterns are everywhere. Managing read-write access is constant. Avoiding deadlock is crucial.
And seeing the different strategies, how Linux adapts, how Windows provides its objects, how OpenMP simplifies things, how functional programming avoids the problem, it gives you a much richer, more robust toolkit for tackling these challenges in your classes and beyond. I remember spending days debugging a race condition once. It would only show up under heavy load sometimes.
Oh, the worst kind. Heisenbugs.
Exactly. It felt like chasing ghosts in the machine. It really makes you appreciate why these synchronization primitives, used correctly, are so absolutely vital.
It truly does. And, thinking about all this, it raises another important question, maybe something to ponder. We've focused today mostly on synchronization within a single computer system sharing memory, using CPU cores on one machine.
Right. Local concurrency.
But what happens when your processes, your tasks, are spread out across multiple machines in a network, a distributed system?
Ah, okay. Things get even harder then.
They certainly get different. How do concepts like transactional memory translate? How do you implement locking or coordination when there's network latency, potential message loss, maybe nodes crashing independently? How do you maintain data consistency and handle failures across a whole cluster of machines?
Wow. Yeah, distributed locks, consensus algorithms. That sounds like a whole other level of complexity.
It is, maintaining consistency and fault tolerance in large-scale distributed environments. Well, that's definitely a deep dive for another day.
Okay, I think my brain is full for today. That's all for this deep dive into process synchronization. We really hope it's giving you some powerful insights and maybe a clearer path forward in your studies.
Yeah, hope it helps you nail those concepts.
Keep learning, keep questioning, and we'll catch you next time on The Deep Dive.